Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about the disruption of equilibrium and Le Chatelier's principle. So let's get into this. So we talked in a lot about equilibrium or dynamic equilibrium in my previous video. And so when we talk about equilibrium, equilibrium is really not something that's really achieved by reactions outside of a laboratory. So most of the time, uh, the reactions are going to be not at equilibrium. Like take for example all of the reactions that are happening in your body. Right, you've got all these equilibrium processes going in your body, and there's never really going to be equilibrium because you've got changes in concentrations of products and reactants. Right, you make reactants in one process. Those reactants are then used in another I'm sorry, those products are used as reactants in another process. So you've got these fluctuation of products and reactants in your body, and so you're not really ever going to reach equilibrium all that often. Or take for example when you take your what is it called, vinegar. Right, you take your vinegar out of the cupboard in your kitchen, and as you're holding your hand, the warmth of your hand is going to increase the temperature of the vinegar, and so you've got that acetic acid equilibrium there, where you have the acetic acid on one side as a reactant, and then on the other side it breaks apart into H plus ions and acetate ions. So when you're holding in your hand and the heat from your hand goes to the bottle, that temperature is causing the forward reaction to increase. And so in that case, you're going to have a disruption in the equilibrium where now, maybe the heat is going to be causing more of a what do you call it? Is going to cause a more of a dissociation or ionization of the um, acid, the vinegar, or the acetic acid in the vinegar. Sorry, I'm stumbling over my words right now. So so there are a lot of factors that we need to think about when we're talking about the disruption of equilibrium. And one of those factors is the changing of concentrations on equilibrium systems. So let's talk about that first, and then we'll talk about temperature and Le Chatelier's principle. And so here we have an example of a reaction that's in equilibrium. We've seen this one before. We have carbon monoxide gas reacting with water vapor to create carbon dioxide gas and hydrogen gas. And so if we're thinking about equilibrium and the disrupting of equilibrium, let's think about what would happen if we increase or decrease concentrations of reactants or products, right? So in this reaction here, if I'm trying to use this reaction to create more H2 gas, hydrogen gas, and I want to produce more hydrogen gas, then one way to do that is to make the forward reaction go faster, right? I need to disrupt the equilibrium to do that. So here I have the system, let's assume it's at equilibrium. So the forward reaction, the rate of the forward reaction is equal to the rate of the reverse reaction going this way. So if they're equal, then I'm getting the same amount of product, carbon dioxide and water, or carbon dioxide and hydrogen gas being formed as carbon monoxide and water being formed in the reverse reaction. Well, if I am in the industry and I want to make it so that more hydrogen is produced, then I need to do something that's going to disrupt that equilibrium and force the forward reaction to go faster. And there's a couple of ways I can do that. One way is I can, um, excuse me, I can add more water vapor to the reaction vessel, right? So water is being used to create more hydrogen, then what I can do to speed up the forward reaction, right? That's one way I can do it. I can either speed up the forward reaction or slow down the reverse reaction in order for more product to be created. So one way to do this is by adding more water vapor molecules. And so, why would that have an effect? Well, if you remember, go back to the collision theory of reactions. And so, remember, reactions are going to occur if you have your reactant molecules colliding with the right amount of energy and the right orientation. So, they've got to collide. Well, if I increase the number of water molecules, then I will increase the number of collisions between water molecules and CO. Well, what is that going to do? If I increase the collisions, then I'm also increasing the fraction of the collisions that are going to be successful. More collisions means more successful collisions, right? Not all of them are going to be successful, but overall, if I'm increasing the number of collisions, then there's going to be a larger fraction of those collisions, or maybe not a larger fraction, but still, I'm going to have more successful collisions than I did before. And so that's going to increase the forward reaction. So this reaction, the forward reaction, is going to increase while the reverse reaction initially stays the same. However, if the forward reaction increases, right, that's going to start to increase the amount of product, right? So then the amount of products form. And again, remember, same reasoning, more product molecules means more collisions. And if I get more collisions of the product molecules, then the reverse reaction will start to speed up. And then they're going to reach an equilibrium again. And so that's shown in this diagram here. So here on the y-axis, I have reaction rates. And on the x-axis, I have reaction time. So here you can see the forward reaction at the very beginning when all I have are reactants. So I take the reactants, I put them in a reaction vessel. At time 0, before there's any time to react, I have a high rate of reaction in the forward direction because all I have are reactants, reactant particles. So then the carbon monoxide and water are going to collide a lot, forming more product. Well, as time goes on, the rate of the reverse reaction is going to start to pick up. Why? Because I'm forming more and more product molecules, and the product molecules will, as you build up more and more of those, there's more likelihood of collisions. So you're going to get more collisions between the product molecules, causing them to go in the reverse direction to reform the carbon monoxide and the water. And that's what you see here. So the rate of the forward reaction is going to decrease. Why? Because as you're using as you're using the reactants to create products, you're decreasing the amount of reactants. Well, if you're decreasing the number of reactants, then the rate at which they react is going to slow down because reaction rate is dependent upon the number of particles you have that are able to collide. So less reactants means less collisions, which means slower reaction rate. So as the reaction goes on, you're getting less and less product. So product is decreasing. So the reaction rate of the forward reaction is decreasing. At the same time, you're building up more and more product molecules. So more product molecules means more collisions. More successful collisions means higher reaction rate in the reverse direction until the rates are equal, and now you have a dynamic equilibrium at this point here. Okay, now that we've reached the equilibrium, we can disrupt the system to then cause the reaction to go faster to produce more product. And I can do that by adding more reactant. I can either add carbon monoxide or I can add water vapor. So I add water vapor. So at this point, the concentration of the water vapor shoots up to a new level, right? Or I should say, I add water vapor to the container, and because I'm adding more water vapor, I'm adding more particles. Therefore, more collisions are possible with water and carbon monoxide. So if I increase the number of water molecules, then I'm increasing the probability of water molecules colliding with the CO to make a successful reaction. So if I add more H2O here, then the reaction rate shoots up. So the reaction rate for the forward reaction is now much faster in the forward direction compared to when it was at equilibrium. So now you're not at equilibrium anymore. The forward reaction is going to be faster than the reverse reaction rate. And so again, now the forward reaction is going to be faster. So you're back at the same thing. So you're going to make more product. As you make more product, you're losing reactants. And so the forward reaction is going to decrease steadily. As you're making more product, then the reverse reaction is going to pick up until it reaches dynamic equilibrium again. So at this point here, you've disrupted the system, and so what happens? The forward reaction increases, so now the forward reaction is faster, so now you're going to be making more product initially compared to reactant. So what we say about this reaction, when we add more water to cause the forward reaction to become faster than the reverse reaction, we call that shifting the equilibrium towards the products. So why? Because we are causing the system to be unbalanced, or such that the forward reaction is faster and the forward reaction is making more product initially until then you reach the equilibrium. So you're going to have a new equilibrium, dynamic equilibrium. So we call that shifting the reaction or shifting equilibrium towards the products. Okay. And so if I summarize this, then what it says is if you increase the reactant concentration, it doesn't matter what reactant concentration, but any reactant concentration, if you increase it, that increases the rate of the forward reaction. Why? Because you've increased the number of particles of reactants that are going to collide and make successful products, right? So remember, the rate of a reaction depends on how many reactant particles you have. Increase the reactant particles, increase reaction rate. So if we're increasing the reactants, we're going to increase the forward reaction rate. Therefore, at the beginning, the reaction rate of the forward direction is going to be greater than the reaction rate of the reverse direction, and therefore the system shifts towards products because we're making more products compared to reactants. Okay, well, there's another way that we can increase the forward reaction. Instead of adding more of the reactant, we can actually take away product. So if we could remove and decrease the concentration of one of these products, then that will have the same effect. The rate will go faster in the forward direction. And why is that? Well, let's look at the diagram here. So, or we could think about it and then we'll look at the diagram. So if we think about it, what's going to happen? So think about collisions again. Let's say if I add something to remove carbon dioxide. So if I remove through another reaction, I can remove carbon dioxide from the mixture, and that's going to decrease the number of carbon dioxide molecules that are available to collide with the hydrogen molecules. If I decrease the number of carbon dioxide molecules that are able to collide, then I'm decreasing the number of collisions. So if I'm decreasing the number of collisions, then that's going to lower the rate of reaction. In this case, the reverse reaction is going to go slower. So in this case, the forward reaction is going to be faster than the reverse reaction, because by taking the reactant or taking the products out, I've slowed down the reverse reaction because I'm limiting or lessening the number of collisions available to make reactants going in the reverse direction. So we can see that here. So here, once again, I have at the very beginning, time 0, the reaction rate of the forward reaction is very fast. The reverse reaction starts at 0 because I don't have any reactants at time 0. As the forward reaction goes forward, I'm creating products. At that moment, as I make products, some of those products are going to collide to reform reactant. So the reaction rate in the reverse direction is going to start to increase, while the reaction rate in the forward direction decreases. Why does the forward reaction rate decrease? Because I'm using up some of the reactants, and as the reactants decrease, then collisions decrease, and then the rate decreases. So then the rate of the forward reaction is going to decrease as the rate of the reverse reaction increases until they reach equilibrium, this dynamic equilibrium. So at this point, what do I do? I remove CO2. So at this point, I remove CO2. So the concentration of CO2 goes down. I'm decreasing the particles of CO2. So I'm decreasing the number of collisions that can happen between CO2 and hydrogen gas. What's that going to do? Well, the reaction rate of the reverse reaction is going to go down, because I've decreased the number of particles that can collide for that reaction rate. So now what's going to happen? I'm going to have the reaction rate decrease. So the reverse reaction decreases, right? So if the reverse reaction decreases, then I'm not going to form as much of the reactant, and the forward reaction is going to go faster. So I'm going to lose temporarily, I'm going to start to lose more reactants and create more products. And so in that case, what is that going to do? If this decreases, then that means the forward reaction is going to steadily decrease. And that's what you see here. So once I take the CO2 away, the reverse reaction rate decreases, therefore causing the forward reaction rate to decrease, because I'm not going to make as many reactants. And so the forward reaction is taking some of those reactants away because it's going faster. So the rate decreases, and therefore the rate of the reverse reaction is going to increase, because I'm going to form more of these products, and so that's increasing these product molecules, increases collisions to make it go that way. So then you're going to reach equilibrium again, and then you get a new dynamic equilibrium. So notice that the dynamic equilibrium before and after the disruption are different. So notice that the dynamic equilibrium here before the disruption compared to here after the disruption. So here, when you add reactants, you end up with a reaction rates that are higher than before, right? But the reaction rates are equal. So the reverse reaction rate and the forward reaction rate are equal, but they're both at a higher reaction rate. And then here it's lower, right? So if I take product away, I have a reaction rate that I started with, and they're both the reverse and the forward reactions are equal with this rate, but then I go down and the new equilibrium rate is lower. Okay, and so in this case, you can summarize this as if you decrease the products, right, that's going to decrease the reverse rate. Why? Because you're taking product molecules away. That's going to decrease collisions. Decreasing collisions decreases reaction rate. Once you decrease the rate of the reverse reaction, that the reverse reaction to begin with is going to be less than the reaction of the forward rate, of the rate of the forward reaction. And so again, that's going to bring us to shifting the system towards products, because initially when you take the when you take product away, that's going to cause the forward reaction to be faster, and that's going to favor making products. So we shift it towards making products. So that's, we say, shifting towards product. Okay, you can shift it towards reactions too in the same way, right? If I wanted to shift this way, then what I want to do is get the rate of the reverse reaction to increase. Well, how can I do that? I can either do that by adding product, increasing the number of particles here, causing the the reverse reaction to be faster because I'm increasing collisions, or I can take reactant away, and then by taking reactant away, I'm slowing down the forward reaction, and in that case too, the reverse reaction will be faster than the forward reaction, therefore favoring reactants. So you can think of it that way too. Okay. All right. So that's it for the effects of changing concentrations. Let's look at temperature and the Le Chatelier's principle. So stay tuned. Okay, so let's talk about Le Chatelier's principle. So for Le Chatelier's principle, it states that if a system at equilibrium is altered in a way that disrupts the equilibrium, then the system will shift in such a way to counter that change. Okay, so simply put, anything you do to a reaction or equilibrium system to disrupt that system, it's going to react in such a way that it's going to undo that change you made. So whatever you do to that reaction, Le Chatelier's principle says it's going to try to undo that. So let's talk about concentrations. So we talked about what would happen if we increase the rate or increase the concentration of H2O gas. What would happen if we took away CO2 gas, and how that relates to increasing or decreasing collisions and leading up to the increase or decrease of the reaction rate and so on. Well, Le Chatelier's principle is kind of a principle that you could use to kind of quickly predict which way it's going to shift based on the change that you make, right? So let's take, for example, if I increase a reactant. So it doesn't matter which reactant I increase. Let's just say I increase the reactant. Well, according to Le Chatelier's principle, if I increase the reactant and I disrupt the equilibrium, the system's going to shift to try to undo that. So it's going to try to decrease the reactant. So if I add reactant, increase the reactant, the equilibrium is going to shift to decrease that reactant. Well, how do you decrease reactant? You take the reactants and make more product. So you're going to decrease reactant to make more product. So that means that the forward reaction is going to increase, and therefore it's going to shift towards product. It's that simple. So Le Chatelier's principle says that if you increase reactant, the reaction is going to shift towards product in order to decrease the reactant that you added. Now, it's not going to decrease it all the way back to the original because, as we saw earlier, it's not ever going to go back to where it was before. It's going to reach equilibrium, but the concentrations are not going to be what they were before. But the concentrations will be such that the equilibrium constant is going to be the same. Okay? So, what if instead of increasing the reactants, I decrease the reactants? Well, if I decrease the reactants, then according to Le Chatelier's principle, the system will shift in such a way to counter that. What does that mean? That it's going to shift in a way to increase the reactants back to where they were, right? So if I take reactant away, then it's going to shift to make more reactant. It's going to want to make more reactant because I took some away, right? So it's going to shift in the reverse direction. It's going to shift towards reactants. You can think of it this way on the product side too. If I increase the amount of product, then the reaction, the system is going to shift to get rid of product, right? So if I add product, the system wants to get rid of product. So how does it get rid of product? It takes the product and reforms the reactant. So it's going to go this way. It's going to favor reactants. It's going to shift towards the reactants, right? If I take product away, if I remove product, then the system is going to want to add that product back. So it's going to want to undo what I did. If I take away, the system wants to add. So if I take away product, the system is going to want to add product. How does it do that? By taking more reactant and forming more product. And that it's that simple according to Le Chatelier's principle. So you can predict which way it's going to shift based upon what change you make to the system or what change is made to the system. Okay. Well, what about temperature? Okay. Temperature works exactly the same way. So you'll notice here that I have energy on the product side. This means that this reaction is an exothermic reaction because during the forward reaction, energy is produced and therefore exits from the reaction system. So it's an exothermic reaction. So in this case, the really easy thing that we can do is we can treat energy just like any other product. So in the same way that we treated, CO2 and H2 as products, energy we can treat the same way. So think about it this way. If I raise the temperature, that's like adding energy, right? How do you raise the temperature of water when you're in the kitchen? If you want to boil water, what do? You put it on the stove, you turn on the heat, you add heat, you raise the temperature. So think of raising temperature as the same thing as adding energy, right? Adding heat, right? So if I increase temperature, that's the same as adding energy. So just like in the same way with the other products, if I increase energy as a product, what does the system want to do? It wants to shift in the direction to get rid of product. So it's going to shift in this direction to try to get rid of the energy that I'm adding, excuse me, by increasing the temperature, right? So it's going to shift towards reactants. So if your reaction is exothermic, raising the temperature will shift towards, cause the equilibrium to shift to the reactant side. Okay. What if I decrease temperature, right? If I lower the temperature, that's like taking heat away, right? If I put something hot into the freezer, the cold freezer is going to take heat away from the substance, right? So because the temperature is lower. So if I lower the temperature, that's like removing energy. So I'm removing product because energy is a product for an exothermic reaction. So if I remove product, what's going to happen? The system is going to react, or it's going to adjust or shift in such a way to undo that. So taking energy away is going to make it shift to make more energy. So it's going to shift forward towards products, right? So that's the way you can understand the how the raising and lowering of temperature will affect the equilibrium. And if the energy is on the reactant side for endothermic reaction, right? If it was an endothermic reaction, for the sake of argument, if we had energy on this side rather than this side, if it was endothermic, meaning that it absorbs energy to go that way, then it works the exact same way. If I increase the temperature, then I'm increasing energy. If I'm increasing energy, the system is going to shift to decrease energy. So it's going to shift this way to absorb more energy. So it's going to shift towards products. If I decrease temperature, that's going to decrease the energy. And if it decreases energy, the system is going to shift to increase energy back up. So it's going to shift towards this way to produce more energy. So it's going to shift towards reactants. So depending on which side your energy is on, if it's endothermic and therefore it's going to be a reactant, or if it's exothermic, it'll be a product, you can use Le Chatelier's principle to predict which way it's going to shift based on temperature changes. And so that's how you can apply Le Chatelier's principle to determine how the change you make to the equilibrium will affect the shifting of the equilibrium. Okay, so one last thing before we finish. The effect of catalysts on equilibria, and that's simple. Catalysts have no effect on equilibrium concentrations of reactants and products, right? So everything else is going to affect the equilibrium concentrations. So remember, before, if I increase or decrease products, or if I increase or decrease reactants, I'll change the concentrations. I'm going to disrupt the equilibrium, but the system's going to adjust to reach a new equilibrium, a new dynamic equilibrium, right? They reach that new dynamic equilibrium, but the concentrations are not what they were before. The concentrations have now changed. Same thing with temperature, right? So if I adjust the temperature, it's going to shift left or right, and that's going to change the concentrations. So the concentrations of products and reactants at equilibrium, at the new equilibrium, are not going to be the same as they were before. Catalysts don't have that effect. So catalysts are not going to affect the equilibrium concentrations of reactants and products. What they do, however, is they speed up both the forward reaction and the reverse reaction at the same time in the same way. So they're not really going to have an effect. There's not going to be a shift to either left or right by adding a catalyst. The catalyst is not going to have that effect. And so that's it for the catalysts. So that's it for the video. I hope you enjoyed the video. If you did, please like the video, share the video, hit that like button somewhere over here or over here. I don't know where. Look for it, hit it. Also, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, if you have a particular question or problem you need help with, put that down below. I would love to do that for you. Thanks for joining me and have a great day.